Use cylindrical shells to find the exact volume of the solid generated by rotating y equals the square root of 4x and y equals x squared divided by 4 about the y-axis. I've already graphed the two functions below. Hopefully we recognize that the top function is the square root function and the bottom function is the quadratic function. Let's go ahead and label them. And because the square root of 4 is equal to 2, we can write the top function as y equals 2 square root x. And let's write the bottom function as y equals 1/4 x squared. Whenever we're using the cylindrical shell method to find the volume of revolution, we want to sketch a representative rectangle that's parallel to the axis of rotation. Because we're rotating about the y-axis, we'll sketch a representative rectangle, let's say here. And now if we rotate this solid about the y-axis, we generate the solid shown below. To see this in more detail, let's take a look at an animation. I've already set this up using CalcPlot 3D. We can see the bounded area we want to rotate about the y-axis. And now let's rotate the area about the y-axis and view the solid. This is the solid we want to find the volume of. Now let's go back and sketch a representative rectangle, which we see here in red. If we rotate just the representative rectangle about the y-axis, we can see why this is called the cylindrical shell method. This is one cylindrical shell of the total volume. So here's the shell, and here is the total volume. And now let's go back to our work and set up the definite integral that will give us the volume. First, notice the thickness of the representative rectangle would be a change of x or delta x. This indicates we will integrate with respect to x. Looking at our notes below, this indicates we'll be using the formula shown here on the right, where we have a vertical axis of rotation. Notice we have a dx on the right. R of x is the radius function, and h of x is the height of the representative rectangle. So going back to our graph, notice r of x would be the distance from the rectangle to the y-axis, which is simply x. And then the height, h of x, is going to be the top function minus the bottom function. So again, to begin, we'll be using the volume formula, v equals 2 pi times the integral from a to b of r of x times h of x dx. R of x is the radius function, which equals x. And the height function, again, is the top function minus the bottom function. Let's write h of x as h of x equals, let's write the square root of x as x to the 1/2. So we have 2x to the power of 1/2 minus the bottom function, which is 1/4 x squared. Because we're integrating with respect to x, we need to determine the x coordinates of the points of intersection here and here, which we can see from the graph will be x equals 0 and x equals 4, indicating a equals 0 and b equals 4 for the limits of integration. If we weren't able to determine the x coordinates of these points of intersection from the graph, we'd have to set the two functions equal to each other and solve for x. And I also want to show this. So again, the square root of 4x is equal to 2 square root of x. Again, the square root of 4x is equal to 2 square root of x. And we set this equal to x squared divided by 4. Next, we'll multiply both sides by 1/2. So we can then square both sides of the equation to eliminate the square root. 1/2 times 2 is 1. On the left, we have the square root of x equals, on the right, we have 1/8 x squared. And now we'll square both sides, which gives us x equals 1/64 x to the 4th. Next, let's multiply both sides by 64, which gives us 64x equals x to the 4th. And now let's set the left side equal to 0 by subtracting 64x on both sides, which gives us 0 equals x to the 4th minus 64x. And now we'll solve by factoring. The product on the right equals 0 when x equals 0, or when x cubed minus 64 equals 0. For the second equation, let's add 64 to both sides. And then we'll take the cube root of both sides, which does give us x equals 4. So we can always find the limits of integration algebraically if we can't find the exact values using the graph. And now let's put all the pieces together and find the volume. The volume V equals 2 pi times the integral from 0 to 4 of r of x, which is x, times h of x, which is 2 x to the power of 1/2 minus 1/4 x squared dx. And now we will simplify the integrand function and then evaluate the integral. Distributing x times x to the 1/2 is x to the power of 3/2, giving us 2 x to the power of 3/2 minus 1/4 x cubed. And now we find the antiderivative. Integrating, we have 2 times x to the power of 5/2 divided by 5/2, or 2/5 times x to the 5/2, and then minus 1/4 times x to the 4th divided by 4, or times 1/4 x to the 4th. Let's simplify the antiderivative. We have 4/5 x to the 5/2 minus 1/16 x to the 4th. And now we need to determine big F of 4 minus big F of 0. Big F of 4 is equal to 4/5 times 4 to the power of 5/2 minus 1/16 times 4 to the 4th. And notice big F of 0 is 0. And now we'll distribute 2 pi and do a little bit of simplifying. Let's write the final volume as 8 pi divided by 5 times 4 to the power of 5/2 minus 32 pi. And because this is volume, this would be cubic units. I hope you found this helpful.